Yesterday we learned, doing a POGL, about Dalton's law of partial pressure. Today we want to get a strict definition of that and also learn how to apply it in some different ways to solve problems. Dalton's law of partial pressures states that the total pressure of a mixture of gases equals the sum of the pressures that each would exert if it were by itself. So in this example, you can see that if we have 4 little blue molecules over here, they need 2 weights to balance the pressure and the volume. If we look at let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 red molecules, they need 5 weights to balance their weight. When we put the blue molecules and the red molecules together, they need the 2 weights for the blue molecules and the 5 weights for the red molecules to balance everything out. And when they have those and they're balanced, their pressure is 10 weights. So it doesn't matter what kind of gas you have or how big or small its particles are. All that matters is the number of moles. So the partial pressure of each gas in a mixture depends on how many moles of that gas are present. We can apply this law in a variety of ways. In this problem, we are looking at a gaseous mixture made from 6 grams of oxygen, 9 grams of methane, CH4, and these are in a 15-liter vessel at 0 degrees Celsius. We want to know the partial pressure of each gas and the total pressure of the vessel. So we need to kind of back this off. So we want to know the pressure of oxygen. So we want to know the pressure of oxygen, and we want to know the pressure of methane. And then, once we have those two partial pressures, we can add them up to get the total pressure of the vessel. So now we need to figure out, how can I find the partial pressure of oxygen and of methane? If we think about what we have available, we have grams, and we have a volume, and we have a temperature. So if we turn our grams into moles, then we would really be in a good spot, because we could use the ideal gas law to find the pressures. So that's what we're going to do. We will start with oxygen. The first thing that I need to do is figure out how many moles of oxygen gas I have. So I'm just going to use my mole map. I'll start with 6 grams of O2. The molar mass of O2 is 32 grams. I found that on my periodic table. And so this means that I have 0.1875 moles of O2. So now that we have our moles of O2, we're in a position to solve for the pressure of O2. So we're trying to find the pressure P. We know the volume, 15 liters. So I'm just using the ideal gas law here to find my pressure. I'm going to plug in my moles that we just calculated. I'm going to use the gas constant, 0.08206. The units on that are liters, atmospheres per mole Kelvin, but I don't have room, so I'm going to leave those out. And then we have 0 degrees Celsius as our temperature, but 0 degrees Celsius plus 273 gives us 273 Kelvin. So I'm going to go ahead and plug in 273 Kelvin. The first thing that I'm going to have to do is simplify the right-hand side of the equation. So I can just restate the left-hand side, pressure times volume. Then I'm going to multiply 0.1875 moles times 0.08206 times 273, which gives me 4.2 liters atmospheres. Now I can simply divide both sides by 15 liters, which shows me that my pressure for oxygen is going to be 0.28 atmospheres. That's my partial pressure for oxygen. We're going to go ahead and do the exact same thing for methane. So methane, CH4, has a molar mass of 9 grams. Oh, I'm sorry, a starting point of 9 grams. The molar mass of methane is 12 plus 4, so 16 grams in 1 mole of methane. If we work that out, we have 9 divided by 16, which gives us 0.5625 moles of CH4. Now we can solve the ideal gas law once again. We'll set it up with pressure, the same volume as the oxygen, the moles for the methane, our gas constant R, and our temperature 273 Kelvin. I'm going to solve for pressure using the same process I used above, which is going to give me pressure of methane being equal to 0.84 atmospheres. The final step of this process is to find that last piece, the total pressure in my container. So to find the total pressure, I'm going to take the partial pressure of oxygen and add it to the partial pressure of methane, which is going to give me 1.12 atmospheres total. And just like that, we have solved a problem using both the ideal gas law and Dalton's law of partial pressures. Let's go ahead and have you try one on your own. In this example, a container has a volume of 8.20 liters, and it contains a mixture of 2.5 moles of H2, 0.5 moles of O2, and enough argon so that the partial pressure of argon is 2 atmospheres. The temperature of the whole flask is 127 degrees Celsius. We want to find the total pressure in the flask. Since we want to find the total pressure in the flask, we need all of the partial pressures. So far, the only partial pressure that we have is the partial pressure for argon, which is 2 atmospheres. We need to find the partial pressure of H2 and O2 in order to be able to solve the problem. So we're going to use the same process we did before. This problem is really nice also because it gave us the mole amounts of hydrogen and the mole amount of oxygen. Go ahead and set up this problem. Your first step is to find the partial pressure of hydrogen and oxygen, and then you can add those to the partial pressure of argon to find the total pressure in the flask. Pause the video, see if you can do that on your own, and then check back in to see if you got the same answer that I did. All right, so now we've calculated the partial pressure of hydrogen, which is 10.01 atmospheres, the partial pressure of oxygen, which is 2 atmospheres, and we already had the partial pressure of argon, so we can simply add these up and solve. So we'll plug in the partial pressure of argon, which is 2 atmospheres, the partial pressure of hydrogen, which is 10.01 atmospheres, and the partial pressure of oxygen, which is also 2 atmospheres. If we add those guys up, we get a total pressure of 14.01 atmospheres, and that's our final answer to the problem.